Hello and welcome back to Let's Code Physics. This is episode 4 of our development of an FTL beam optimizer. So FTL is a game where you face off against these squarish looking ships, and one of the weapons you can get is a beam weapon that makes a cut across the ship. Different beams come in different lengths. You get to pick any starting point on the ship and any angle, and so it presents you with this really interesting geometry problem of how to best align your beam. Which you can do lots of trial and error, but that's also something we can use a computer for. And so I've successfully created this FTL beam optimizer, which is getting more and more optimal thanks to the feedback I've received from the kind folks on YouTube and Reddit. I want to give a big thank you to everybody who has given feedback. This has generated a lot of great responses. I've been just inundated with them, and it's been really great. I've learned a lot of new tricks from it. I've thought about the program in different ways, and the program you see today is definitely a lot better than it was last week, thanks to the feedback I got from a lot of folks. So I just want to go through three major changes that I've made in the last week. The first is just a few cosmetic changes. One of the first things that I did was I fixed the rounding issue. So you notice I was having a little trouble with snapping the rooms, especially when I get over here into the negative into the negative quadrant. So when you get into quadrant 2 here or quadrant 3 down here, it was having a little trouble snapping into place. That's because I had my rounding set up with positive numbers in mind. I did not have rounding set up appropriately for negative numbers, and so they were snapping funny. And so now it's much smoother. It snaps more into place with what you think it would do. So that's the first thing I did, was I fixed the rounding issue. Another thing I did, since I was having to find the edge of rooms so often, so when you're firing these beams, you're usually very interested in where the edges of the rooms are, because you're usually going to start at an edge and maybe try to creep up into a room just inside the edge. And so I was having to do these edge calculations over and over and over again. So I went ahead and made functions for those. Let me see if I can find those now. Right edge. Yeah, so I defined a few functions for those. I even streamlined it compared to how I had it originally. And so basically, to find the left edge of a room, it's just the room's x position minus half its x size. So the position is always at the center. So the size is the width. So the left edge is halfway to the left. The right edge is halfway to the right. So the only difference between right edge and left edge is this minus sign becomes a plus sign. And then bottom and top work the same way. You've just got y's instead of x's. So the edge finding is a little bit easier now. I've also, you might have seen, I've incorporated that into my rope simulator code that I'm developing on Wednesdays. I've also fixed some of the clicking issues. You remember before, if you clicked on delete a room and then you clicked not on a room but out in empty space, the program would freeze because it didn't know what to do. Now it just resets that button, and so you're able to just continue on. So that's also a way, if you accidentally click this and realize you didn't want to delete a room, then you can click an empty space and it just reverts things back to normal. And I also took into advice, I especially discovered this after I started using the optimizer program while playing, that you really need to have the rooms highlighted at the end of the code. So previously it was just drawing the line representing the beam, and you were left wondering, is it in that corner? I can't quite tell. Let me pull up a picture from one of the users. Yeah, so for example here, it's difficult to tell whether it's hitting that room, whether it's hitting that room. So it's difficult to tell where you're supposed to start it. This actually brings us to the second issue that I've addressed in the optimizer, which is this issue that that Redditor Meclaws, laddie. This user thought that this was a cool program, said it took a long time to process. Is that just your PC being slow? No, that wasn't just your PC being slow. It was taking a couple minutes on my end as well. I just cut that part of the video for entertainment purposes. Attention maintenance purposes. There we go. So he said that he tried it on one of the hardest beam placement. Unfortunately, it didn't work. And so what he was looking at was on this Mantis aggressor ship here. where my code failed. My code was only picking up 1, 2, 3, 4, 5, 6 rooms, and the optimal beam he found was 1, 2, 3, 4, 5, 6, 7 rooms. He was able to solve that later on by changing the dx. So currently the dx, the amount it's changing the beam location each time, is 0.2. He found that by opening the code and changing that to a 0.1, you end up with getting that winning scenario. The reason for that is because when the code is looking at where to start in a room, it originally started in the corner and then moved over by dx, and then moved over by dx, and then moved over by dx, and then moved over by dx until it reached the next corner. And the ideal beam for that situation was starting right about here. So it was starting in between two of the dx's. And so you can even see it in the image over here. You know, it's starting just above halfway there. It's starting just about just off of halfway from the midpoint of the room. And so by excluding that point, it was missing an entire room's worth of beam. That gives you an idea of how sensitive this beam weaponry is and how precise you have to be with your aiming, that just by being that much off, by being, by splitting the distance in half, you can get an extra room. And so his solution, Miklaz's solution, was to say, well, I guess you need to change, that is not what I wanted. I guess you need to change the dx to 0.1 so that way you can cut this thing in half. Now, unfortunately, that's going to make the code run 4 times as long because the dy, the y grid, is separated by that same amount. So by cutting the markings in half on both the x and the y, you're doubling the amount of time it takes to go this way and doubling the amount of time it takes to go this way. And Miklaz noted that by saying, either dx equals 0.1 or you change d theta or both seem to fix it, but now it's at a crawl speed, so it goes even longer. It goes from a few minutes to lots and lots of minutes. But I was able to figure out a compromise to that because the issue isn't that you need to go through through having the dx. You just need a better starting position for a scenario like that. So what I was able to do is I was able to say, okay, we're still going to go in by a dx of 0.2, but we're going to start at the edge plus 0.1. So if you imagine I've got a distance there, then I just have double the distance there, and then half the distance in here, and half the distance in here. So each of these spaces is a dx, but then this space between the edge and the next one is a dx over 2. That actually makes a lot of sense because you don't really want to try to start in the corner of a room. You want to start kind of off from the corner so that way you can angle it better. And so the way I optimized, or the way I implemented that in the code, let me see, how did I write this thing? Here it is. I gave this change a comment in all capital letters. So Miklaz, this is the change you were looking for. So we're keeping dx and dy up here as 0.2, which keeps the code running on the order of a minute or two. And we start by looking at the edge plus half of a dx. So it's taking, one fewer steps. It's not quite starting at the edge. It's not quite getting to the other edge, but it's capturing that interesting behavior there that's near the edge. So I think that's a good compromise there. And that reduces the runtime of the code. Well, it doesn't reduce, it does reduce the runtime of the code, but it does successfully get this ship. You notice I brought this ship up. So it is redemption time. So this was the answer that was proposed before, and so I'm going to run the optimizer now, and we're going to see if we get Miklaz's corrected solution over here. So the optimizer has finished running, and you can see it does successfully pick up on Miklaz's arrangement there, going from the lower left-hand room here, sneaking up and hitting both of these 2 rooms in the corner there. So that's a total of 1, 2, 3, 4, 5, 6, 7. So just by making that little adjustment, by having it start in a different place, I haven't sacrificed any efficiency, and I've gotten a better answer. Speaking of efficiency, another thing I've added to better understand where I can improve the efficiency of the code, I've added in some timer commands. So I've added in the time package to Python. It tells me that the entire run took 88 seconds, so a minute and 20 seconds. A little bit shorter than I was getting before, thanks to some changes we'll talk about in a second. I don't know what went wrong with this time calculation here. I need to go back and fix that. So ignore that negative number there. But basically, it takes it took less than a hundredth of a second at the beginning to create a set of points to consider. We'll get into that in just a minute. And the bulk of the time is spent checking on rooms. The bulk of the time, 85 of the 88 seconds, is spent checking whether rooms have been hit. So that's my next goal, is to make that process a bit more efficient. But it is down from last week, thanks to the third thanks to the third change that we've made. The third change comes as a suggestion from FTL, which sounds like the most awesome power chord I've ever heard on a guitar. Let's see, we got to talking about, some ways to make it more efficient. This viewer suggests you could probably pick 2 rooms and see if the beam could possibly be long enough to connect them, and if it is, see how many rooms it could hit on the way, or something like that. So that I took that idea and I ran with it. So the way my loop runs now, instead of looping over all of space and saying, well, let's try every single point it can possibly start at and just loop around every possible angle it can loop around, the way I set it up was to always start in a room and always end in a room. And in fact, it's only going to consider starting at the edge of a room, because there's really no point in starting not at the edge of a room, because you can always slide the beam over and hopefully cut into a little bit more. So that's where this loop comes in here. This part where it's selecting points to begin and end at. And what I've done is I've set up a beg list and an end list. And basically what it does is, based on the geometry, the code decides whether it's going to look at the top, bottom, left, or right edges. So for example, let's suppose it's looking for beam arrangements that can go from this room number 1 here to this room number 2 here. Right. So if the rooms are arranged in that way, then I only want to consider points that are along the top edge of room 1 or the right edge of room 1. There's really no point to considering rooms along the bottom edge, because any of those beams are going to pass through the right edge or the top edge anyway. And I'm only interested in beams that come through the left edge of room 2 or the bottom edge of room 2, again, because any beams that cut through the top edge are going to come through one of those anyway. Any that come through the right edge are going to cut through one of those anyway. So I'm only considering points along here and points along here. Now, based on the observation earlier about this dx over 2 business, I'm really considering points that are a little bit in from the edge, right? We don't want to start right at the edge, because you can't really click on the edge. There is the beam splitting along the edges trick, which I still need to implement. Well, actually, I'm going to try it out in the game first, see if I can see how well I can reproduce it, so that I can understand it. But that's basically what this does here, is if these conditions are met about the relative positions of their top edges and bottom edges, then it's going to run along the bottom edge of number 1. If this set of conditions is met, then it's going to run along the top edge of number 1. Same thing for the left edge, same thing for the right edge, and then it does the same type of check for the end points of the beam. Well, not really the end points. Think of it as the points that it's aiming at, because the beam may be longer than that, right? So the two rooms may be arranged like this, but let's say that the beam is this long so that it can cut along this way. Well, then that's still a good beam, right? We're still interested in going from this point to this point, but then we're interested in seeing, how many rooms there are in between those two and farther along the beam this way, right? So you can kind of imagine, that's kind of a weird looking ship there, a little staircase pattern, but you can imagine, you want to check along the beam for other rooms. So now we're only looking at beams that are guaranteed to hit at least 2 rooms. So the way we check that is we loop around, excuse me, we loop around the beginning room, so we're no longer looping over all of space, over all the x coordinates and all the y coordinates. We're now looping over the rooms, and then we're looping over the ending rooms, and we're only proceeding with the check if the location of the two is less, if the distance between the 2 points is less than or equal to the beam length. So basically, if the beam can't cut between the 2 points we're looking at, then there's no point in considering that combination. This is cutting down on the computer time significantly. Then what it does is it calculates the theta between the two. So it's using the rise over run, just like you do in Algebra 2 for the slope. So instead of incrementing over theta, I'm now giving it 2 points and having it calculate a theta. Let's see, the score evaluation works the same way that it did before. Let's see. Oh yeah, this is another cool thing I did. Coming up in just a second. Sorry, I'm going down my list to make sure I have some kind of logical progression, or at least more logical than it would be if I were just ad-libbing it. And so what it does now is it's checking, it's looping over all the rooms and saying, okay, does this point hit the room? Does this point hit the room? Here's another improvement I've made, which is to cut down on the amount of time that it takes checking for whether those rooms have been struck. So basically, previously the way it was happening was it would be moving along this beam here to it saying, okay, is this point inside a room? Yes, okay, good. Is this point inside a room? Yes, okay, good. Is this point inside a room? Yes, okay, good. Except the problem is all three of those points are in the same room, right? So once you've checked this first point, there's really no purpose in checking until you get outside of the room, right? It's wasting computer time to check all these points along here in the room. So what I've done is I've made another change where once it establishes, let's say the beam, we're evaluating the beam up and to the right. So we start in room 1, we head toward room 2. Once it establishes that there's been a hit in this room, what the code now does is it skips all the other points until it reaches a point outside of that room. And then it's going to continue incrementing forward. Once it reaches another room, it goes to the edge of that room, continues incrementing forward. Once it reaches this room, it's going to jump to the edge of that room, and so on and so forth. The way I've implemented that, let's see, here's all the scoring business. Oh no, this did not screw things up. This screwed things up earlier today. This is the part of the code where it figures out where to go next. I've got lots of layers of indent here, as you can tell. Basically what it does is it's checking for whether you're well within the room. So I found there was a little bit of a glitch if I only checked if it was inside the room. What I really need to do is check it within a little bit inside the room. So that's why it's xb minus left edge is greater than dx. So it's within, so if it's more than dx away from the edge, that's basically what that means. So we're considering points that are inside this region. We're not considering points that are in this border around here, because then it's a little too iffy to tell whether it should jump along or not. In particular, it messed up Miklos's scenario that was presented. But basically what it does is it says, okay, here's the X you want to try next. You want to move your Y all the way to the top edge. Let's say that the place it's headed for is the top edge. Like, for example, in room 2 here, you would just jump up to the top edge. It says, okay, here's the next X to try. If that works, that's basically what this is checking, is has it taken you way outside the room, or has it taken you to the edge of the room? Basically, if it hasn't taken you outside the X bounds of the room, then you make the next X those values. Same thing here. If the thing is going downward, then you want to jump to the bottom edge. And here's the next X and the next Y to attempt. Same thing if the room is narrower. So like, for example, in I don't really have a good example of it. Let's suppose that I had a room that was like this, and my beam was coming in at this angle. You would want it, once you've established that it's hit this room here, you would want it jump to this point, and this point is at the right edge of the room. So instead of setting the try next Y first, you would set the try next X. Trinex. Boy, it's been a while since I played Legend of Zelda: Link to the Past. That was a cool boss, Trinex. Basically, you snap this one to the right edge and then calculate the next Y to try. Or if it's headed the opposite direction, you try the left edge and then jump the Y position to its next thing. So you see these little print statements here where I was calculating the number of steps it saved. These can save on the order of like 8 to 20 steps, depending on, you know, how wide the room is. 8 to 20, that seems high. It's something on the order of like 8 to 12 or something like that. It cuts down on the steps by a pretty decent amount. And so that way it's not checking the same point and getting the same answer over and over again. And so that's been pretty cool. That also, of course, has led me to look into the calculation times. And so now we've only got 85 seconds of room checking instead of several minutes of room checking. So I'll be looking for further ways to streamline this room checking process, because that's still hogging most of the computer time. So again, I want to thank everybody for all the feedback that they've given me. Thank you also to everybody who gave me feedback on my playing strategy. I was definitely not out to demonstrate optimum playing strategy. My goal was to demonstrate the use of the code. I will be sure to strike the shield room first using the halberd beam from now on. Thank you so much for that. I also got suggestions for creating some standardized layouts so that you don't have to click and drag these blocks over and over again. Trust me, I've created this ship about 100 times in the last week. Nobody's looking forward to that more than I am. That sounds like a wonderful project to crowdsource. So I will post an update sending out a request for people to create their favorite ship in the FTL Beam Optimizer and send me a little code snippet that I could include, and then I'll put your name in the author credits, so we get to share a little credit or something like that. So thank you again so much for all the feedback. This has been a very fun project. I'm going to continue to tinker with this. I will also update the self-contained executable file for this so that people can continue to try it. When I find or receive feedback from you about other ways to optimize the code or other ways to streamline the code to make it more efficient and run a little bit faster, I will post updates on that. If you'd like to receive updates about the code as I go along, please send an email to letscodephysics@gmail.com. And I'll gladly send you an email whenever I post an updated version of the software. The next thing we're going to do for Fun Friday, we're going to put this one on the back burner for a little bit, and we're going to take a look at what would it take physics-wise to actually create a lightsaber? What kind of power source would it require? We're going to do a little bit of coding, figure out what type of math you need to create a lightsaber, and then see how that translates into the physics involved. And that'll be timed in time with the release of The Force Awakens on DVD, Blu-ray, app stores, and however else we're watching movies these days. So thank you again so much for watching. I will see you next time. Bye-bye.